Lecture we have seen the following. So if we have a region which is bounded above by the graph of the function fx, bounded below by x-axis, bounded on the left hand side by the line x equal to a, and on the right hand side by the line x equal to b, and we are given a solid which is obtained by rotating this region about x-axis. So we have seen how do we compute the volume of the solid using disk method and washer method. Here we are given a different scenario. So again we are given the same region which is bounded above by the graph of the equation y equal to fx, and we are asked to determine the volume of the solid which is obtained by rotating this region about y-axis. So this is our y-axis and this is our x-axis obviously. So how do we compute this? We could use our motivation that we have taken, that we have seen in washer method. So we could use these lines and generate washers around y-axis. When these lines are rotated around y-axis, they of course give you washers, and you could use them to find the area, find the volume of the solid that we are concerned with. However, there are some computational difficulties, so let us look at it. How do we go about doing the washer method in this case? So here we would like to take this region on y-axis, so this interval on the y-axis, and we are going to compute the area of the whole region, and we are going to subtract the area of this region. But you see, when we come to this uh, this interval in y-axis, there is an obvious problem. Namely, here we have to compute, we have to write x as a function of y, and what is that function going to be? That function is going to be f inverse y. But even if we know that in some cases where f is a bijective function, it is not always easy to determine the function as determine the inverse of the function f. So this gives us a huge difficulty in terms of computing the volume of such kind of a region, and that leads us to our next method, which is called cylindrical shell method. So here what we are going to do, we are not going to use washers like this here. Instead, what we are going to do is that we are going to take rectangles which approximate the region that is on the xy plane somewhat one of the rectangles should be somewhat bigger than the region, and one of the rectangles should be somewhat smaller than the region, and then we are going to rotate these rectangles about y-axis to approximate the volume of this region of the solid that we are concerned with. So roughly speaking, let us look at pictorially how those things will look like. So here I have taken a small region which lies between the point x and x plus small x delta x on the x-axis. So the volume that is generated by rotating this region under the curve, we call it delta V, and let's see if we can approximate delta V by the by rotating these two rectangles. So first look at the yellow rectangle. So what happens if we rotate this? So we are going to get a cylinder minus a small cylinder. So what I mean is that, so this line is going to give me a circle or a cylinder first, and then this line when rotated about y-axis will give me a somewhat bigger cylinder, but the part in between which is here is missing. So this is somehow caught between these two cylinders that we have got. And how do we compute the volume of this kind of hollow cylinders that we are going to see just in a moment. But let us first complete our picture. So we have this yellow rectangle which, when rotated around y-axis, gives me a picture like this, which is the big cylinder here, or the big hollow cylinder here. So when we take the red rectangle here, this will give me a somewhat small hollow cylinder, and we can see that our volume, which is given by our solid, which is generated by the small portion of the graph here, gives me a solid which is caught somewhere in between these two hollow cylinders. In particular, is delta V is caught in between these two quantities. So first, this is the volume of the big hollow cylinder, and it is also bounded below by the volume of the small hollow cylinder. So I am writing though because I am referring to the picture what I have just drawn. So can we compute this volume? Okay, we can. So again, let us look at this picture. Suppose this refers to our yellow cylinder. So we have, so what we have to do, we have to do area of base times the height. And what is the height of this yellow cylinder? So for this, we have to look at this line, the length of this line, and if this point, the x coordinate of this point is x plus delta x, the height of the cylinder is definitely going to be f of x plus delta x. So the height of the cylinder is f of x plus delta x. What is the height of the smaller cylinder? This is going to be simply f of x, as you can see, because this is a line which is drawn on the point small x on the x-axis. So this cylinder has height f of x. So what is the base of the region? What is the area of the base of the cylinder? This is always constant as in constant for the big cylinder and the small cylinder. So let me try to compute it. So here we have a circle whose radius is given by x. We also have a circle, the big circle, whose radius is given by x plus delta x. So what is the area which is between these two circles? This is simply going to be pi of x plus delta x whole square minus x square. So this is the area of the base. So the area of the base is given by this quantity. Height is different in these two cylinders. For the yellow cylinder, it is given by f of x plus delta x, and for the smaller cylinder, it is going to be equal to f of x. So if we want to summarize, then the volume of the bigger cylinder is given by the area of the base times the height of the cylinder, and volume of the smaller cylinder is again area of the base times height of the cylinder. So in principle, what we have shown is that delta V is now caught between these two quantities that we have written down here. So this quantity and this quantity, volume of the big cylinder and volume of the small cylinder. Some cancellations happen in the parenthesis. You can see that x square gets cancelled with the x square here, and we are left with a very nice expression. So we can take delta x out, and inside we will be left with 2x plus delta x. Same thing will happen here, because the base of the area of the base of the cylinders is constant in the two cases. And for the right hand side, the height of the big cylinder is f of x plus delta x, and here the height of the cylinder is f of x. Now for ease of computations, we will here assume that the function that we have taken, fx, is continuous. So that I have mentioned here also, but let us go on. So now if f is continuous, and if we want to take the limit as so now what we do is that we divide the whole inequality by delta x. So we Assume that delta x is not equal to 0, and that is delta x is greater than 0, because this is the length of our interval on x-axis that we have just taken. So we divide the whole inequality by delta x, and now we take the limit of those three things as delta x tends to 0. The interval, the size of the interval tends to 0. On the left hand side, it is quite easy. So delta x goes to 0, so then we are left with pi times 2x times fx. On the right hand side, we are left with pi times 2x, and here since f is continuous, we see that f of x plus delta x goes to fx. Since f is continuous, limit as delta x tends to 0, f of x plus delta x is equal to fx. This is the definition of continuity. And then if we now take the limit as delta x tends to 0, this also goes to pi times 2x times f of x by sandwich theorem. But we know from our differential calculus that limit delta x tends to 0, del v del x is nothing but equal to dv dx. And if we know that dv dx is this quantity pi times 2x times fx, then from the fundamental theorem of calculus, we know that v is equal to the integral of this function dv dx as x goes from a to b. So what we have just derived is that volume of the region that we were concerned with is given by v, where integral runs from a to b, 2 pi x fx dx. So we are going to see two examples using how to use this formula that we have just derived. So first we start with something that we have seen previously, but not exactly here. So here we have taken the line which joins the 2 points, namely origin and the point h comma r. So the line is given by the equation y equal to r by h times x, and we want to so this gives me a triangle here. I want to rotate this triangle about y-axis, and I want to determine the volume of the resulting solid. And now after we have done all the hard work, it is very easy. We have to just put in the formula. So here fx is exactly this function, r by h times x. So the volume of the solid is given by integral from 0 to h 2 pi x fx dx. And if we just do the computation correctly, we will see that the formula turns out to be equal to 2 pi rh square by 3. So note that this is not equal to the volume of the cone that we had started our journey with. So remember, the volume of the cone was 1 by 3 pi r square h, but this formula is somewhat different. Next, we are going to look at a somewhat different example. So here we are given a region which is bounded above by the graph of the equation y equal to 2x minus x squared and bounded below by x-axis. So this is the region that we are going to have. And so first let us determine where this graph of the function cuts x-axis, and for that we have to just put y equal to 0. You can see that if you put y equal to 0 in this equation, you are going to get x equal to 0 or x equal to 2. So that means that the points on the x-axis are given by 2 comma 0, so y equal to 0, x equal to 2, and 0 comma 0 origin y equal to 0 and x equal to 0. And now if we want to compute the volume of the solid which is obtained by rotating this region about y-axis, we just have to use the formula that we have derived in our previous slide. And if you do all the calculations correctly, you will see that the volume is equal to 8 pi by 3.